This is the second video for chapter 14 from the McGraw-Hill chemistry. It's mixtures, solutions, and concentration. So we're going to continue on, and 14.3 is the factors affecting solution formation. 3 or 4 important points that we're going to hit here. Some that I don't have written up in the notes, but things that you'll read in your text and that you'll have questions about in your quiz. When solutions form, the process that happens is called solvation, and solvation is where a polar compound, whether it be polar, molecular, or ionic, surrounds the opposite charges and kind of rips them apart. So NaCl, when it goes into solution, water, the negative end of water, the O, grabs onto the plus Na, for instance, in NaCl, and the H's, the H plus, grabs onto the Cl minus. So that actually helps to keep the particles in solution, and that process is called solvation. One of the demos we did in class was that I did a supersaturation with sodium acetate trihydrate and dropped a crystal in, and it all solidified just like that because it was holding too much solid at the cooler temperature it was at. We heated it, and it dissolved everything right after we were through. So heat makes solids dissolve more in solutions. Gases are just the opposite. This is a question on your review. It's in your text. It's also one that you'll be asking on the quiz or the test, that when you heat up a solution, less gas is generally dissolved, but more solid. So solids and gases are kind of opposite each other there. It's the reason why in the heat of the summer, in the shallow pond, fish sometimes will come up and gulp air because there's not enough oxygen in the water. Since it's so hot, it's not holding as much oxygen. Also the reason why, if you're a fisherman, put a little bit of ice into your bait, and that makes the bait stay alive longer. It slows down their heart rate, but it also puts more oxygen in the water. So cold solutions hold more gases. Hot solutions hold more solids. And that's in general. There are always some exceptions. When we did that demonstration, I dropped the little crystal in, and it all solidified. And this heat, this is how some of the hand warmers are made. I handed it around. Everybody said, "Oh, that's really hot." That heat is called heat of solution. And I also mixed a little bit of sodium acetate and water, and when it dissolves, it's an endothermic reaction, and it was cold. When it comes out of solution, it's hot. So it's kind of like a wheelbarrow for energy. You load it up, takes heat out of your hand when we make the solution or out of the burner, and then when it comes out of solution, when we drop the crystal in, it gives the heat back out. Endo and then exothermic. So we're going to move on. The factors that affect solution formation, there are 5 questions or 5 answers in your review that come from this, and it's just logic more than anything else. You're trying to mix some tea. How do you make the sugar dissolve faster? You stir it. So agitation or stirring. Surface area. Big surface area is equal to small particle size. So we have a big cube of sugar. We drop it in. The water can only, or the solvent can only get to mostly the outside. But if we break that up, then the water liquid can get all the way around it, so that the smaller the particle size, the more surface area. So that would be one and the same. On your review, you can either say large surface area or small particle size. Think about what dissolves quicker, a sugar cube or powdered sugar. Of course, powdered sugar would. Temperature. You want to get more to dissolve faster, you heat your tea up, and sure enough, it will dissolve faster. Nature of the solids. If the solids are like oil and water, they're not going to mix anyway, so it has to be mixable or miscible. One that's not up here is pressure. For gases, the more the pressure, the faster solutions form. You can see that by a soda. So you'll take a soda, and when you get it, look at it, you don't see many bubbles, but you open the top. When you open the top, you release the pressure, and a lot of the bubbles will start coming out because it can't hold as much CO2 when there's not the pressure pushing that CO2 in. You release the lid, you release that pressure. Solubility. So when we talk about a solution that doesn't have all it can hold, it's unsaturated. It could have a little bit and be dilute, or it could have a lot and be concentrated, but if it doesn't have all it can hold, we say it's unsaturated. Saturated would be at that temperature, that's all it can hold, and if you put another crystal in, it'll either precipitate or it'll drop to the bottom because it can't hold anymore. Supersaturated is what we did on the demo with the sodium acetate trihydrate. I put all that could be held, and then we heated it, and then we put more in, and we kept putting more in when it was heated until no more could happen. Then I heated it a little more, and then slowly cooled it, and it cooled, and it forgot that it was holding too much until we dropped the crystal in, and then all of a sudden it just all dropped out, and you saw that it all solidified. They make hand warmers like this. There are several stores that sell those, but Heat Solutions online, you could get these hand warmers, and there's a little clicker, and when you click it, it sets up a shock wave that causes it all to come out of solution. Throw it in boiling water, and it's a reusable hand warmer because once you boil it and let it cool, it's ready to go again. So that's supersaturated. Henry's law, S1 over P1 equals S2 over P2. Solubility 1 over pressure 1 equals solubility 2 over pressure 2. This should look just like a gas law that we did in the last chapter because it is a direct proportion. It's a ratio. So generally we're going to be solving for solubility 2 or pressure 2, and you can either cross multiply to solve these. This is just really algebra. You just plug in, solve for the one thing you don't have. You'll have 3 of the 4 variables. But what Henry's law says is that solubility is directly proportional to pressure. So if I put pressure on the soda, this is how they make soda. They put CO2 in, then they pressurize it, and then they put the lid on, and it keeps the pressure and thus keeps the CO2 pushed in the solution. When you open the lid, it bubbles out. You see the CO2 bubbling, and that CO2 adds something to the taste, a little bit to the taste, and I guess the texture when you drink it, so people like that. So there's a practice problem there, and I have lots of these practice problems online and also available in class for you to try them out. And some of them are step by step by step so that you can actually solve them and then look at the answer and see what you did wrong or what you did right. So that's Henry's law, and I will give that to you on your possibly useful page. Colligative properties. Way to think about colligative property is collective properties of solution and solute. So I take water, and the normal boiling point for water is 100 degrees. But when I add a little bit of salt to it, the boiling point goes up because it's trying to escape. The water, when you heat it up, is bouncing around, and it's got lots of energy, and it's just getting ready to escape, and then salt grabs onto it and keeps it in. So it has to have more energy to escape. In other words, higher temperature, more energy to boil. And some recipes ask you to put a tablespoon or teaspoon of salt in, like when you're boiling eggs or something, so that it will boil faster. It doesn't really explain that. It just says add a teaspoon of salt, especially if you're at higher altitudes, because remember, the higher you are, the lower the boiling point, so it doesn't get as hot. You add a little bit of salt, you make up for that, and it will boil maybe at 100 degrees or maybe even higher. So the colligative properties are that when you add salt, the high one goes higher and the low one goes lower. Those are the 2 easiest ways to remember. The boiling point goes up, the freezing point goes down. When you throw salt in the ice, when you're making ice cream, it can get to 13, 14 degrees below zero. And it has to be in order for ice cream to freeze. Because ice cream is not pure water. It's mostly water, but it's got, milk has some solutes in it and a little bit of sugar and cream and things like that. So it has to be below zero to freeze, and putting salt in makes it below zero. It's also why they put salt on roads, because the salt makes the water freeze below zero. So let's say it gets to 0 degrees, ice starts forming, they throw salt on it, now it forms at, say, 10, 12 degrees below zero, and it won't form ice because it has to be colder. So sand will do the same thing. Plus, sand and salt, they give you a little bit of grit to help you get traction. So they have kind of a dual purpose. The other colligative property I want you to know is that vapor pressure goes lower when you add salt. Vapor pressure is already low for water because water holds on to the other water molecules and doesn't let it go in the vapor space unless it gets enough energy. When there's salt holding on too, now you got water and salt holding on. The water doesn't go up there, even less of the water goes up. So boiling point goes up, the high one goes high, the low one goes low, freezing point goes down, and vapor pressure also decreases. Colligative properties continued. There are two formulas here, and they're both almost the same. Delta T is the change in boiling point, delta T sub B, and delta T equals Kb times M. And the Kb is a boiling point constant that's always the same for water. And we're probably going to use water most all the time, but I give you a chart on your possibly useful that has all the Kbs and Kfs you will need. So the Kb for water is 0.512 degrees Celsius per mole. And of course, it's delta T equals Kb times M. M is molality with the L, the little m. Remember molal, little l, little m? And that is moles per kilogram of solvent. So when you solve this, you're going to probably be given, you'd be given the Kb, it's for water in most cases, and you'll be given the amount of moles and the kilograms of solvent. Remember, a lot of times it'll be in milliliters or grams of water, and you have to convert that to kilograms. A milliliter is 1 gram of water. And of course, the freezing point is the same thing. There's two main differences. One is that the Kb and the Kf are different for substances. Kb for water is 0.512 degrees Celsius per mole. For Kf, water's Kf is 1.86. Also, remember that when you solve for delta T, that's not the new boiling point. That's just how much the boiling point changes. Take 100 for water and add your delta T to 100. That's the new boiling point. For freezing, 0 is the normal freezing point for water. Take the delta T sub F and subtract it from 0. So you're going to have a minus freezing point once you add something like salt to water. One other thing that you need to consider, and this is important, and it's on all the practice pages that I have, is that if it's an ionic compound, it splits into parts. If you had NaCl, for instance, there's one more number you got to multiply by, and that's times 2, because there's double the particles. So the ionic compounds, this is largely why they use salt up north. It's available. There's places where there's salt mines where they can get it freely, and it has kind of double the effect. Also washes away quicker, and the sand is kind of there to stay, and you kind of have to bulldoze, pick it up and scoop it, where the salt kind of dissolves better. There's an ecological impact of that. One, your cars corrode. The other is that salt goes into the surrounding fields and areas, and that some of the grass and the plants don't do well with that salt. So the page 500 and 502 are the boiling point and freezing point charts. That's where you can look up the K values. And there are practice problems there, and I also have practice problems online, probably 10 or 12 of them that deal with boiling point and freezing point. So I recommend that you do those. So we'll finish up talking about osmosis and osmotic pressure. If you got the notes, I bumped this to the C set of notes because just to help kind of balance out the information. Osmotic pressure is a pressure caused by a difference in concentrations in solutions. For instance, inside our cell and outside of our cells. And we usually draw a picture of a cell in a beaker, and then that way you have the inside the cell and outside. Where there's more solids, the water is a lower percent. Well, it makes sense. If you have 100% water, there's no solids. So if you put a cell into pure water, the cell has some stuff inside and some solids, so the water is going to be 100% water, and osmosis says that water flows across a semi-permeable membrane from a high to a low concentration. So the 100% water, it's going to flow from there into the cell, and the cell can never be 100%.
Mr. Perez, please call the front office.
The cell can never be 100% because it's got stuff in it, right? It's got organelles and sugars and proteins and stuff like that. So the end result of a cell going in pure water is it's going to explode. It just pop unless it's got some way to prevent that. And there are lots of ways that cells are able to survive in situations like that. But our cells that are used to being maintained by a process called homeostasis, our cells, if we put the blood cell in the pure water, bursts. Water goes in and it gets bigger and bigger because the osmotic pressure, and that's what osmotic pressure is. It is the pressure that causes these cells to get bigger. So the other term, and the thing I think important on this osmotic pressure or the osmosis, is that when you draw a cell, this is what I want you to be able to do every time you have one of these questions where you're going to either name the hypertonic and hypotonic solution or decide which way the water goes, is to draw a beaker with a cell inside, and if the problem says inside you've got 90% water and outside you've got 100% water, the last thing you need to do before you answer the question is write the other percent. If 90% is water, 10% is solid. 100% is water, there's 0% solid. Now, to name the solution, you're going to look at the solids. 10% solid is greater than 0, so this is the hypertonic. Think of tonic being solids. It's not really the way it translates out, but hyper means lots, like hyperactive. So the 10% is the hypertonic solution, and the 0 is the hypotonic solution. Hypo means low, like hypodermic, goes under or low, under the skin. So that's how you name the solutions. And the water always goes from high to low water. So 100% to 90, this cell would get bigger. Now, I may ask you to name the hyper and hypotonic solutions. I may ask you which way the water goes. Or I may ask you, does the cell get bigger? Does it get smaller? Water goes in, cell gets bigger. Water leaves, like if there was salt out here, then a cell would shrivel up. If you drop a grape into salt water, it shrivels up and looks like a little bit like a raisin because the water goes out of the cell. So that's the questions about osmotic pressure and hypo and hypertonic. So, come in for help if you need help on that. That finishes up the B set of notes. And, if you need to practice some of these, we didn't work any practice problems here because I've got a load of those out on the website, and there's a bunch of them available in class. So you should go through those and try to work as many as you can. Come in for help. Come in the mornings for help or possibly lunch. Good luck, and work lots of problems.